Hi everyone. In this lesson, we're going to talk about the part 2 on the thermal properties of matter. So let's go into the content of this chapter. So we have already learned in the first part about the difference between internal energy, specific capacity, and latent heat. Okay. So basically, in this chapter, we're going to use these ideas to look at the heating and cooling curve of water. Okay, it is very interesting to view all this information on the heating and cooling curve, because the ideas of kinetic and potential energy, the ideas of melting, freezing, boiling, and condensation, and the ideas of heat capacity and latent heat are all reflected on the curve itself. So if you know where to apply what, this topic will be very simple to you. Okay, so after we have looked at the curves, the next thing is I will try to solve some real life problems that you will encounter in your examination or your test. Okay, I've divided into 3 different types. The first types are for simple one stage process questions. The second type are the multiple stages one, which involves temperature changes and change in state. Don't worry about all this jargon, I will explain later. And the last one is on the heat exchange between two bodies. Okay, so this one is more brief explanation. I'll probably be giving another lesson, another video on more complicated examples. Okay, but we'll see how it goes. So first of all, let's look at the heating curve of water. So imagine you have ice at minus 20 degrees and you heat it up. Alright, so this will be roughly the curve. So you expect that the ice will heat up until 0 degrees where it melts. Then after that, it heats up again as water until 100 degrees where it boils. And then finally, it becomes steam. Okay, so let's look at each individual part, A, B, C, and D. Alright, so first of all, region A. Region A is where ice increases in temperature from minus 20 to 0 degrees. In this region, there is only solid state. There is no liquid or whatever. Okay, and heat is supplied, okay, to increase only the kinetic energy. So I want you to pay very, very close attention to especially this part about kinetic and potential energy and heat capacity. Alright, so A is using kinetic energy, increase in kinetic energy, and also number 2, heat capacity formula is applied. Okay, and the energy gained by the substance is mc delta theta. Now, if I compare this with region B, alright, region B is when ice melts to form water, but the temperature remains constant at 0 degrees. Okay, the mixture of it is a mixture of solid and liquid. So here is solid and liquid. So in the melting process, solid and liquid coexist. Okay, and heat energy is supplied to increase the potential energy. See the difference? Okay, in A is kinetic energy, in B is potential energy. Now, the next one is latent heat formula is applied to find the energy gain, which is Q equal to mLF. Okay, let's go to C. Now, for C, water increases temperature again from 0 to 100 degrees. And then liquid, it is in liquid state. Okay, and then next, the energy supply is used to increase the kinetic energy again. So now it's kinetic energy again. Alright, and then next, the heat capacity formula is applied again. Q equal to mc delta theta. And last, region D is when water boils to form steam at a constant temperature of 100 degrees. The mixture is liquid and gas. Okay, the heat supply is used to increase the potential energy only. And latent heat is formula is used Q equal to LV. So in short, we can look at the region in two ways: kinetic versus potential, as well as heat capacity versus latent heat. Region A and C, and also this region which we seldom consider. Alright, so we just have to consider A and C for this moment. Region A and C are regions where the temperature increases without a change in state. Alright, so region A and C, because it is only a temperature increase without a change in state, the change for region A and C is only kinetic energy. Potential energy, no change. Now, when kinetic energy changes, you only use specific heat capacity formula. Alright, so A and C, kinetic energy, and A and C, specific heat capacity formula. Now for B and D is a region where there is only a change in state, but there is no change in temperature. Now because there's no change in temperature, there's no gain in kinetic energy, but there is only gain in potential energy. So in B and D, it is potential energy only, but no kinetic energy. The formula to use is the latent heat formula. Alright, for B and D. Understand? Now, let's look at the cooling curve. Okay, the same thing applies. Even without going through the information, you know that this is condensation, this is cooling down, this is freezing, and this is cooling down of the ice. So once again, let's look at the information. Region A, steam condenses to form water at a constant temperature 100 degrees. So it's a mixture of liquid and gas state. And heat energy, okay, be careful here. Now this is energy release, not absorbed. Okay, when you're heating, energy is absorbed. When you're cooling, energy is released. It has to be the opposite direction. Now heat energy is released and it decreases potential energy, because this is potential component. Potential energy decreases, not kinetic energy. Now latent heat formula applies. Region B, water cools from 100 to 0 degrees, decrease in temperature, liquid state only. Okay, but there's no change of state. So heat energy reduces or decreases, the kinetic energy only. And heat capacity formula is applied in region B. Now next, region C, water freezes to ice at a constant temperature of 0 degrees. The mixture is solid and liquid state only. Solid and liquid state together. And heat energy is released to decrease the potential energy only. And latent heat formula is applied. Okay, and finally, region D, ice decreases in temperature from 0 to minus 20 degrees. It is only in solid state, and so heat energy is released to decrease the kinetic energy, and the formula is using heat capacity formula. So in summary, we can actually summarize into two main categories. For heating curves, energy, so the first category is, this is very important because a lot of students will always forget. When you're talking about heating curves, when you're heating some substance up, energy is absorbed by the substance. So kinetic and potential energy increases. But if you are talking about cooling curve, energy is released by the substance and kinetic and potential energy decreases. Alright, so this is the first key information you need to take away. Now the second thing that you need to take away is this: when temperature changes without a change in state, which is the rising and the falling part of the curve, okay, only kinetic energy increase or decrease. Alright, heat capacity formula applies, okay, and the substance remain as a single state substance. Example, solid ice is heating up, liquid is heating up, or liquid is cooling down. Alright, this is a single state condition. So these are the three key information. They are always linked to each other at these states. Alright. Now the next thing is, when there's a change in state without a change in temperature, that means the horizontal portion of the graph, only potential energy increase or decrease. Okay. latent heat formula is applied. Q equal to MLF for both boiling and condensation. Q equal to MLV. There is a typo here. Q equal to MLV Q equal to MLV applies to both boiling and condensation, and Q equal to MLF for both melting and freezing. Okay, and the substance exists in two states. During the process, when it's melting, it exists as solid and liquid. When it's boiling, it exists as liquid and gas, and temperature remain constant. Okay, so let's move on. Okay, so as I mentioned, I want to talk about the solving the problems in terms of one stage problem or two stage problem. So let's go to the first one stage problem questions. One stage problem question refers to questions where the substance only undergoes one change of state. Okay, so let's and is usually very easily applied using one single formula. So let's just give you an example of what's a one stage problem. Okay, for example, what's the energy required to raise 5 kg of water from a temperature of 30 to 50 degrees? Simple, right? Okay, so how I'm going to solve it? I want you to pause the video and try it first. Okay, I believe that you have finished already. So first of all, you ask yourself, is this a change in state or is it a change in temperature? So if it is a change in temperature, you need to apply the specific heat capacity formula. Alright, if it's a change in state, you need to apply the latent heat formula. So in this case, it's a change in temperature, so it's a specific heat capacity formula. So first of all, you will write down the formula MC delta theta, and then you sub the value. M is the mass, C is the specific heat capacity of water, and then delta theta is a change in temperature. Okay, one thing you need to bear in mind is that the change in temperature has to be always the higher minus the lower. Okay, you don't care what is the order, whether it's increasing in temperature or decreasing in temperature. You just take the higher value minus the lower value, because the change in temperature must always be positive. Okay, if not, you will have a minus sign here, which is very strange. Okay, bear in mind. I repeat, delta theta has always to be positive. So use the larger value to minus the smaller value. Okay, so I hope you got this answer correct. Let's move on to the next question. What's the energy released when 400 grams of water at 0 degrees freezes to ice at 0 degrees? Okay, I'll pause the video for a while. So have you solved? Okay, basically, same thing again. You ask yourself whether this is a latent heat or heat capacity question. So basically, this is a latent heat question because there is only a change in state without a change in temperature. Alright, so you will use the formula Q equal to MLF. Now, M, be careful because it has to be in terms of kg. So in this case, it is 0.4 kg multiplied by the LF. So your answer is 133,600 joules. Okay, now for solving of multiple stage problems. Now, if you talk about multiple stage problem, it refers to problems where there is two-stage processes that has happened. For example, water that is heated to boiling point and the water is completely boiled off. So there's a two-stage process, or it could be even more. Alright, so in this case, you will need to use both the specific heat capacity as well as the latent heat formulas. Now, I can give you an example now. What is the energy required to completely melt 200 grams of ice, which is initially at minus 20 degrees? Okay, I would like you to pause the video and try it on your own first. Okay, have you solved? So what happened is that when you see this kind of question, one of the helpful thing that you can do, which I would suggest you do, is to draw the heating or cooling curve. Now, if you draw the heating and cooling curve, the curve actually provides a lot of information for you that you can really make sure that you answer your question without making any mistake. The first thing is that you know that the ice initially is at minus 20 degrees and it will heat up to 0 degrees. So the change in temperature in the first case is 20 degrees. And you know that this is a heat capacity portion. And for the second part, when it melts, it is a latent heat portion. So you know there is two stages using different formulas. Now once you got to know this, you can actually safely apply the formula of these two stages, MC delta theta and MLF, to solve for the question, which is 3,600 joules. Now let's move on to the next question. What is the energy released when 3 kg of water at 40 degrees cools down and freezes into ice and reaches a final temperature of minus 30 degrees? So I want you to pause the video and try to do it now. Okay, I hope that you're finished. So again, if you draw the curve, you will understand that this question is a 3-stage question: Q1, Q2, and Q3. Now, what is the difference? Straight away from this graph, you know that Q1 and Q3 is a change in temperature, Q2 is a change in state. During a change in temperature, you use MC delta theta, and during a change in state, you use MLF. Alright, so let's work out the answer now. You know that it is going to be the addition of 3 stages, but you have to be a bit careful here. Although their masses are the same, the specific heat capacity of water and ice are different. So in this case, you need to specify your symbols well. Okay, apologies, delta theta is also different, so you need to also specify the delta theta well. Okay, so let me just make sure of this. Okay, so let me just go back to here. So the delta theta is also different because the change in water temperature and the change in ice temperature is different. So these two formulas, although they are MC delta theta, you need to make sure that the differences are highlighted. Okay, so if you sub all the values inside, okay, you will realize that the answer is about 1.695 million joules. Okay, now another question is when you have a case where there is a heater supplying heat to 500 grams of water at the initial temperature of 50 degrees. What is the time taken to boil off all the water? Okay, so you can pause the video now and try it. Okay, I hope that you're finished. So first of all, you draw the 2-stage process again. It is heating up to 100 degrees and then after that boil. So it's 2-stage. Now if it's 2-stage, that means that you will have MC delta theta and MLV. Okay, so from there you work out is 1.235 million joules. After that, you need to know that the heat energy supply is from a heater. So heat energy in terms of power and time is going to be power times time. I repeat, power times time will give you the heat energy supply. So the power times time, which is heat energy supply, will be equal to the heat energy absorbed by the water, assuming there's no loss of energy. So using this formula, you divide, you get 618 seconds. Now finally, I want to talk about heat exchange between two bodies. In fact, the previous question is a little bit like heat exchange between two bodies, but this is a little bit more specific. When two bodies of different temperatures are put together, heat lost from the hotter body while the heat gain from the cooler body until they reach the same temperature. You must remember from the previous chapters on thermal temperature, you have learned that every object, when they put together, right, they want to reach thermal equilibrium. When thermal equilibrium is reached, both bodies have the same temperature. All right. So we can assume that no heat is lost to a surrounding for this kind of questions. Okay, and sometimes one body or both body undergoes through more than one stage of change, maybe temperature change and change in state. Okay, but to make things simple, I'm going to just introduce you to one simple question, which is this one. Okay, 200 grams of copper at 500 degrees was placed in 2 kg of water at 20 degrees. What's the final temperature of the mixture? Okay, you may want to pause the video now. Okay, so now let's solve the question. Again, I propose that you also draw the heating and cooling curve. Now, for this kind of question, you're going to have a case where you have two curves in the same diagram. The cooling curve of copper and the heating curve of water. But what's very interesting is this. The two curves will merge. The reason why it will merge is because both lines both material wants to reach thermal equilibrium. And they will actually merge at exactly the same point. Okay, so let me just illustrate how the diagram will look like. It will look something like this. Now, because we have to make an assumption that the water doesn't boil, then in that case, it's a single stage process for both copper and water. Copper is cooling down from 500 degrees to the unknown temperature theta, while water is heating up from 20 degrees to the unknown temperature theta. So this becomes my heating curve for water and cooling curve. And you realize that when it reaches a certain time t, the two lines coincide. Once they coincide, it will be a straight horizontal line because there's no more heat exchange. All right. So with this graph, right, you realize that it tells you everything already. First of all, you know that there's a change in temperature. When there's a change in temperature, there's no change in state. So you are going to use heat capacity formula. Okay. Secondly, you know what is the change about 500 to theta and theta to 200. So if you write down the formula, it's going to be heat loss by copper equal to heat gain by water. So again, you need to make sure that you use the different symbol for each. M1C1 delta T1, theta 1 for copper, and M2C2 delta theta 2 for water. Now, if you put them together, just one very, very important side note is this. Again, as I mentioned many times, the delta theta has to be the larger number over the smaller number. So in this case, it's 500 over minus theta. Now, on the other hand, for the water, it's theta minus 20. So be careful. In these two cases, the theta is at a different position. This one is subtracted by theta. This one is theta is being subtracted by 20. So regardless, you need to have theta at, you need the value here to be positive. If it is not positive, your answer will be wrong. Okay? So you realize the graph actually helps you because visually you know that theta has to be positive. Theta has to be more than 20, while theta has to be less than 500. Okay, if you work out the formula, you realize the answer is 24.4 degrees. Okay, so this is actually the last question for this part. I may come out with another video on more complex examples. Okay, but at this point in time, I'd like to sign out from here. If there's any queries, you can post it on my blog and to share anything that you want me to explain. Okay, so that's all for now. Thank you and have a nice day.